last video that I made was not using the PowerPoints from the text. It was one that I made on my own. I decided to go back to the PowerPoints. I just felt like maybe that would make you more comfortable. However, if I get feedback from you that you like the other just plain docery type videos without the PowerPoints better, I will be glad to go back to those. This last section of the chapter talks about ionic compounds, which is the other major type of chemical compounds. There are three main types. There's the covalent or molecular compounds, which we just learned how to write their formulas and names. Then there's these ionic compounds, and then there are metallic compounds. And we will not have to write names or formulas for metallic compounds. Those are exactly what they say. They are bonds that form between metals, and they don't actually form true bonds, so you would not name them. A metallic bond would form between, say, atoms of aluminum or atoms of copper, and they don't form bonds. Their electrons form this pool of electrons that are homeless, basically, because their atoms, their protons are trying to get rid of them. They don't want them, because it's all about stability with atoms, which we're going to talk about a little bit more. We talked about the octet rule, but remember, that's what it's all about. And so their electrons, there are those extra electrons that are trying to get rid of, are roaming around, and they're basically looking for a place to go, and so they form this sea or pool of electrons that are floating around, which is good for us because that flow of electrons allows us to have electricity and current. So we are able to harness that and use it for our good. But this section of the chapter 2 talks about ions, and there are two different types of ions that we're going to specifically focus on, and then we're going to talk about how those ions get used to form ionic compounds. The first type of ion that we're going to talk about is an ion that's formed from a single atom, or an atomic ion, and then from a gang or a group of atoms, a polyatomic ion. And then we'll talk about naming them. And then this text really focuses on something that's called oxoanion, which are just anions, or negatively charged ions that contain oxygen, and they are a special class because oxygen is so important. And then acids that contain those anions. And then hydrates. Hydrates are exactly what they sound like they are. When we hydrate ourselves, we drink water. And so they are compounds that have water built into their structure. And then we're going to talk about, just very, very briefly, it's not going to be a major part, inorganic compounds. So the first thing that we're going to talk about are ions that are formed from a single atom. And we're going to talk about just briefly why that happens. Please keep in mind the octet rule that we discussed before. And every atom wishes to have that octet, that especially stable noble gas configuration. And in order to do that, it would like to find its closest noble gas, and the example that's given here is sodium. And sodium has 11 protons. If you'll look on the periodic table that's in your textbook in this chapter on page 48, it shows you that the closest noble gas to number 11, sodium, is number 10, neon. That's where this comes from. So the closest noble gas there, number 10, neon. What does sodium need to do to become like neon? It needs to lose that one electron, and then it's going to have that extra stability. So if it could just get rid of it, that's what makes these group 1A alkali metals so incredibly important and so incredibly active. They have that one extra electron in their outside energy level, their valence shell, and they're going to lose it. And the quicker they can lose it, the quicker they can become stable like a noble gas. And that's exactly what's going to happen. And if you lose something that's negatively charged like an electron, then you're going to become positive. And if you now have a charge, you can no longer be called an atom, because atoms must be neutral. And so they gain a positive charge, and they're called ions. And a positively charged ion is called a cation. Since it loses one electron, it has a positive 1 charge. And you would write its formula as being Na with a +1 charge. And then on the next slide here, it talks about anions. And an anion is one that has gained electrons so that it can become like a noble gas. And again, I would take you back to the periodic table. If you'd look there on page 48, or a periodic table that you have hopefully printed off from the internet or from the blackboard that I provided for you, you're going to see chlorine. If you'll find chlorine, atomic number 17, you're going to see that its closest noble gas is number 18, argon. And number 17, chlorine, is just 1 electron away. Remember, it is the electrons that govern the behavior of the element. Protons identify what the element is, but it's the electrons that govern the behavior. So if it could, it can never actually turn into and become argon, but it can behave like it chemically if it could just gain 1 electron. And so that's exactly what's going to happen. It's going to gain that 1 electron, and in doing so, it gets a net negative charge, so it's now called an anion. And so we would say chlorine with a -1 charge, and now it becomes, we call it chloride. We change its name. If it gains, it also gains a new name, so we now call it chloride. Sodium, right here, remember it lost an electron, so it became positive because it lost something that was negative, and if you lose negative, you're going to become positive. So it has a now positive charge. That's how you write its charge, and it's called sodium ion. This one is chloride ion, and if you then put these two together, you get ordinary table salt. Okay, it is called an ionic compound because it's made of these 2 ions, a cation and an anion, and that bond forms because of the opposite charges of these 2. Opposites attract, and those are attracted by their opposite charge, and that's exactly what happens. All right, and then if you have elements that, oh, I didn't mean to do that. These that are located inside here, in these orbitals right here, these families or groups, especially your halogens here, these are always going to have a -1 charge. These are always going to have a -2 charge. Okay? These are always going to have a -3 charge. These are always going to have a +2. Always a +1. However, these that are in this block, in your transition metals here in the middle, they can have more than 1 charge. And now we're going to talk more about that when we get into electron configurations. But suffice it to say that it's all about stability and what's going to make that electron the most stable that it can be. That's what it has to do with. So let's just take, I think that the next slide is going to use manganese. Let's go there. Yeah, it uses manganese. There are actually 3 different possibilities for manganese. And so since you can have more than 1 charge for manganese, and manganese in your periodic table is number 25. It's like if you know 3 different guys named Bob or 3 different guys named Mike, you got, this is atomic number 25. you've got to come up with a way to distinguish between them. Okay, and so you got to think about these Roman numerals here in the middle, like so, as being like, if you Bob W or Bob R or Bob whatever, it's part of their name. You have to include it as you're naming them. And this Roman numeral tells you the charge. That's what it represents. It is not like in molecular compounds. It does not tell you how many of those atoms there are in the compound. Instead, it tells you the charge. That's what it tells you. That's a very important distinction. Please make sure you get that distinction. Please make sure you get it. Okay? Because when you name these and write their formulas, you must make sure that you include them. Now, this slide tells you about an older nomenclature system that was called the classical naming system. And I'm really not going to spend hardly any time on that at all, because we are only going to concern ourselves with the stock naming system. But it used to, in the classic naming system, when they used the Latin names, they, instead of using the Roman numerals to represent their charges, they used the OUS for the lesser charge and the IC for the higher charge. And that presented itself with a problem with compounds like manganese. What are you going to do when you have 3 of them, like manganese does? There's no OUS and IC. So the stock naming system is what we use almost exclusively today. And there are a few compounds, like an iron, it happens to be one of them, ferrous and ferric, that still fairly common to see compounds named with these suffixes, us and ic. All right, so let's talk about naming them. As I was saying, if you have, you never change the name of the cation, the positively charged ion. In a compound, first of all, it always comes first. The cation always comes first. The positive charge always comes first. And then in the anion, it's going to go last, and you always change its name to IDE, right? And this monatomic anion means it's just, these are for binary. You have one cation and one anion for a binary compound. 2 elements only in the compound. All right. That's what it's talking about. And then you have these things called polyatomic ions. Polyatomic ions are exactly what it says. Poly means many atoms. Polyatomic ions are groups of ions that are covalently or molecularly bonded together, but they're so tightly bound that they go around as a group and they cannot be separated. So they exist almost as a single entity, and they're very difficult to separate, and so they are named accordingly. And almost all of these are anions. Most all of the polyatomic ions that are known are anions. As a matter of fact, there's really only one that is a cation, and I am going to expect when you take your midterm for you to know these, not all, but many of these polyatomic ions. Let me show you the ones I'm going to expect you to know. I'm for sure going to want you to know ammonium along with its charge, not just the name. I'm going to want you to know ammonium, and I'm going to want you to know that its formula is NH4 and its charge is a positive 1. Okay, acetate is another one that's quite often used. Acetate, C2H3O2, and its charge is a negative 1. Then we move on to the next slide. Lose this. And we have the ones with the higher charges. Again, I'm not going to ask you to know all of them, but I will ask you to know the most common. I will ask you to know carbonate, which, by the way, is one of those that we were talking about. It's an oxo anion. Then we have chlorate, which you will not have to know. But these two right here, these are what we're talking about with oxo anions. You have chlorate and chlorite. They both contain oxygens, and they're both anions, but one contains more oxygens than the other. So one gets the word ate and one gets ite to it. They're not ones I'm going to ask you to know, though. I will ask you, however, to know hydrogen carbonate, because it's important in many medical type things, and it's important. It's baking soda. It's what baking soda is made out of. It's sodium. Hydrogen carbonate is baking soda. Hydroxide is a very, very important one that's used often. So I would ask you to know that one as well. And then I'm going to move to the next screen. On this screen, I would ask you to know, here's some more of those oxo anions. Nitrate and nitrite are oxo anions, but I only want you to know nitrate. It's much more common. All right, and then I want you to know phosphate and sulfate. Sulfate and sulfite are more of those oxo anions that we were talking about. Okay, I believe those are all of the ones I'm going to ask you to know. I want to be sure I haven't missed any on the next page. Yeah, that's it. Those are the most common ones that I want you to know. Now let's talk quickly about how you go about naming and writing formulas for compounds. Again, it's all about neutrality and stability. That's what it comes down to. And this is a really, really good illustration of how an ion forms into a compound. Here you have sodium with its 11 electrons out here, and it really wants to lose that one electron so that it can become like neon. Here, chlorine really, really wants to gain that one extra electron so that it can become like argon. And now you have two ions, this one having an overall positive charge, this chloride having an overall negative charge, and now you have opposite charges. And those opposite charges attract each other. And because of that opposite attraction, they form a very strong bond. And that bond is called an ionic bond, or a bond between ions. And that is how ionic compounds form. And they're named very, very simply, and the formulas are very simple to write as well. You write their formulas and their names very simply. You simply name let me see if I keep forgetting to put it in writing mode. Name the cation, in this case aluminum. This was aluminum ion. This is the name of this ion, aluminum ion. Notice it had to lose 3 electrons to become like its noble gas. I'd like to show you that really quickly, even though I'm running short of time. Aluminum is number 13. Its atomic number is 13. If you look on your periodic table, either the one on page 48 or the one that's in your book. In your book on page 48 or the one that you have. It is atomic number 13. The noble gas that's closest in number to number 13 is neon, number 10. What does 13 have to do to get to number 10? So that it can be stable and act like neon, it needs to lose 3 electrons. It will lose those 3 electrons, and when it does so, it becomes a positive 3 charge. So it now becomes aluminum ion with a plus 3 charge. That is how it becomes an ion. Now it is aluminum ion, and it's Al with a plus 3 charge, which I've already written that right there. Okay, oxygen, this oxide right here, that means that its closest noble gas also happens to be neon. Aluminum has this +3 now. Oxygen has this -2. And notice what they've done here. They crisscrossed these. Okay? And technically what they're doing is all about becoming neutral. It will take, mathematically, if you were to write these as fractions, 3 times 2 is 6 and 2 times 3 is 6. So they've got to balance out and become equal. Okay? And then to name it, you simply write the name of the cation, you write the name of the anion, aluminum oxide. For polyatomics, you must not separate them. This phosphate, you have to consider this as being a single atom. PO4 will stay together. It will not split apart. So if you need more than one of them, it has a -3 charge. And so calcium with a +2, phosphate with a -3 charge. The name is going to be calcium phosphate. The formula Ca3, because phosphate has 3. You don't take the charge down. You're just saying, how many of these phosphates would I have to balance out that +2 charge?